Hello everyone, today we will go for this F15 test 5 and you can see that this test 5 actually consists of chapter 16.3 I think up to 16.9. Now your test will be from 16.1 to 16.9. Okay, yeah, let's start. Wait, what happened with my handwriting so ugly? Number one, let E be a solid bounded by a cone above XY plane. Let's see what is that solid. One of the challenge in this last test is like, can you see an equation and figure out what it is? Okay, this is C equals to 4 minus 2R, right? Okay, so when we graph that, suppose this is R and this is C, 4 minus 2R looks like this. Okay, and then you revolve around the z-axis. Now you can see the cone, right? Now, the hint for this question is use divergence theorem. So I actually tell you what theorem to use to compute this surface integral. But surface integral over the closure or the boundary of a solid E, so this is supposed to be E here, of f dot ds is equal to triple integral according to divergence theorem, right? Triple integral over solid E of divergence of f dot ds dv. So let's first compute the divergence of f. Divergence of vector field f is equal to the derivative of the first component respect to x, that will be y squared, plus the derivative of second component respect to y, that's 0, and the third component respect to z is x squared. X squared plus y squared, that's equals to r squared, right? Okay, because later on we will do this in polar or maybe cylindrical integration. Okay, now so the triple integral over E that we are talking about will be x squared plus y squared dv, which if we make into cylindrical integration will be 0 to 2 pi 0 to 2, right? If we solve for c equals to 0, then the r will be 2. And then the c will be from 0 to 4 minus 2r, r squared, r dc dr d theta. Since the integral is independent of theta, then the outer integral will becomes 2 pi. Okay, integral from 0 to 2 r cubed times 4 minus 2r dr. That will be r to the fourth minus, that's r to the fourth, 2/5 r to the fifth from 0 to 2. That will be 2 pi r to the fourth will be 16, and then 1 minus 4/5, 1 minus 4/5. Okay, that's 1/5 there, so that's 32 pi over 5. That's for question number 1. Question number 2. Let a goldfish ball S be part of the sphere. So this sphere here is r squared plus c plus square root of 3 squared equals to 4. So the center is 0, negative radical 3 with radius 2. So I believe the ball actually this one. That's the ball. That's the fishbowl. Okay. With the vector field, that use Stokes' theorem to evaluate the curl double integral over surface S or curve of vector field F dot directional surface oriented surface S, and we will do outward orientation, which means the orientation is going outward like that. Okay, but if we think that way, then if we use Stokes' theorem, so double integral over surface S of curl of F dot ds. Okay, take a look on this part here. If we see from above, then the orientation of this boundary will be clockwise. Okay, what is the radius when c equals to 0? So x squared plus y squared plus 3 equals to 4. Oh, that's actually a unit circle on the xy plane, huh? Okay, r equals to 1. So I will parameterize that using rt equals to cosine t sine t 0. The thing is, like, if I do it this way, it will be counterclockwise. I want to make it clockwise. So what should I do? What should I do? Let's put a negative here. How about that? Put a negative here. Okay. Then it will become clockwise, right? Where the t is from 0 to 2 pi. Okay, so according to Stokes' theorem, this will be integral over c, closed curve, right? This is our c here, of f dot dr. Okay, and so r prime t will be negative sine t, negative cosine t.
Professor, how do we know it's going clockwise?
Based on the orientation of that fishbowl. You see, the fishbowl looks like this, right? And when we say it's a outward orientation, means the orientation of on this surface supposed to be going down. Can you imagine that? Like the water, if you imagine you put water into here, and the water then will go out that way, right? It means the outward orientation implies on that surface is actually going down. Can you imagine that?
Yeah, I could see it.
Yeah.
So we had inward orientation, it'd be going counterclockwise?
In this case, yes, in this case. Now, it's different from if the fishbowl is actually upside down. If the fishbowl is actually upside down, like this, for example, and if it is outward like that, then it implies for the fluid to go out from there, then it means the fluid needs to go in from the bottom, right? But in from the bottom means it goes up. Therefore, the orientation will be upward in this case, and therefore it's positive. The orientation will be counterclockwise. Okay, Now the one here, because it is outward from the bottom, right? Outward from the bottom, it means then the fluid needs to go into this surface so that it can go out from there. That's the way I think, though. That's the way I think. Okay. Now,
Thank you.
and then let me continue. So going to that, continue from there. So what is my vector field F? If I use RT, that will be negative sine T, negative cosine T, e to the xz, but the z equals to 0, which is 1, right? Okay, no, I should not write it that way. And therefore, when I do f dot dr integral over closed curve of c equals to integral from 0 to 2 pi, okay, negative sine t times negative sine t dot r prime t, that's sine squared t. Oh, sine squared t plus cosine squared t plus 0 dt. Is it right? Imagine if you do the dot product. Okay, which is basically equals to integral from 0 to 2 pi of 1 dt. That's just 2 pi. See, if you set it up correctly, then the work becomes quite easy. Okay, now, by the way, that's the first method. I think I should give you the second method. This is method number 1. Okay, method number 2, if I do double Stokes. Double Stokes. Notice that the C, the curve C, is also the boundary for this yellow plane here. Okay, in other words, double integral over s of curl of f dot ds is equal to double integral over d, the yellow plane, okay, of curl of f dot ds. Now, can we compute what is the curl first? Let's do it fast here. I wonder if I can do it in a very small space. The curl of f will be 0, comma, let's see, respect to x, that's z e to the c xc, and then plus 0. But the c equals to 0. What am I doing? That's 0 anyway. And then the last step will be negative 1 minus 1. So negative 2. Okay, while the surface D is normal to, surface D is normal to 0, 0, negative 1. Notice that it is downward, right? The orientation is downward. So the dot product will be double integral over D of 2 dA. That's 2 times area of D. But D is a unit circle, right? The area is pi, so this is 2 pi. Okay. As I remember, I picked this question from one of USC department final. As I remember. Yeah, one of the USC department final. I don't remember which one though, but I know it's, as I remember, it's from USC. Okay, so here I actually provided you 2 different ways to do it. One way is the Stokes theorem, the way the question asks you to do, and the second way is the providing double Stokes theorem. Okay, Remember, we can use double Stokes theorem if first the vector field is continuous on the region containing the fishbowl and larger than the fishbowl. Second, if the boundary happen to be shared by another plane or another surface whose normal factor is a lot nicer. Okay, then at that time you use Stokes theorem. Okay, I think I write this name here incorrectly. Now that's for number 2. Let's go to number 3. Determine whether or not vector field F is conservative. Well, to know it is conservative or not, vector field F is conservative if and only if the curl of vector field F equals to vector 0. Okay, so that's what we are checking now. Curl of vector field F equals to I, J, K of dou x, dou y, dou z of 2xy x squared plus c squared 2yc. And for the x component, that will be z 2z minus 2z, that's 0. The y component is negative of 0 minus 0. And the c component will be 2x minus 2x, which is vector 0. Therefore, vector field F is conservative. Now, once vector field is conservative, then we can find the potential function, right? Let f x y c be its potential function. Then this f must be integral of p dx, right? Integral of 2xy dx, that is x squared y plus a function of yz. Okay, now don't forget that plus a function of yz. On the other hand, vector field F must be also integral of q dy, which is integral of x squared plus c squared dy. That's x squared y plus yc squared plus a function of xz. On the last part, integral of r dz is 2yc respect to z, that's yc squared plus a function of xy. Now we do comparison. So the potential function must be, let's highlight this. This guy match with this must be this guy, right? On the other hand, this guy here match with this must be this guy, right? A function of yc. So we don't have the function of xz. It must be the constant then. Okay, so the potential function must be x squared y plus yc squared plus a constant. Let me use k instead. Okay. Did I underline them? Okay. Part B. With the same vector field, compute this line integral for RT. Now, don't forget that this vector field is conservative, right? Okay, it's conservative. So the integral over C of f dot dr is equal to, due to the fact that the vector field is conservative. Let me write it down properly. The vector field is conservative. That must be equal to the potential function at the terminal point minus the potential function at initial point. Okay, so you don't even need to do the r prime thing. You can, but why? Okay, now then what is r1? Let's see, r1 is 0, 2, 3 minus r0 is 1, 1, 0. Now we plug in numbers. So this will be x equals to 0. So this will be 0 plus 2 times 3 squared minus 1 squared times 1 plus 0. So this will be, what's that? 9 times 2, 18, minus 1, that's 17. Okay, now you can try doing it the wrong way, but I don't think that's a good idea. Number 4, suppose we have that surface RU phi, where the U and phi is a unit squared, 0, 1, 0, 1. Find the surface area. How to do the surface area? Area of surface S is basically double integral over S ds, as I remember, right? But the ds then translated to be double integral over d of the magnitude of r sub u cross r sub v dA. Okay, so what we need to do is find the r sub u and r sub v and then do the cross product. R sub u will be 1 phi 2u. R sub v will be 0 u 0. So the cross product will be Ru cross Rv will be negative 2u squared 0 u. Am I doing okay? Make sure. So the magnitude of this Ru cross Rv will be, I can factor the u out and then square root of 2u squared plus 1. So that's u square root of 4u squared plus 1. So the area of that surface S will be double integral over d of magnitude of Ru cross Rv dA, which is double integral, actually 0, 1, 0, 1, 0, 1, 0, 1 of u square root of 4u squared plus 1 d phi du. It's a rectangle, right? So you can do du d phi, it will come up the same. And integral over 0 to 1 of d phi will be just 1. So we basically do this integral. U square root of 4u squared plus 1 du. I need to do substitution. W equals to 4u squared plus 1. dw equals to 8u du. So this becomes integral from 1 to 5. Okay, and w dw over 8. So 1/8, 1/2 w squared from 1 to 5. So 1/16, 25 minus 1, that's 24/16 reduced by 8, that's 3/2, 1.5. Okay, that's for number 4. Now again, I say this in my Calc 2, I also say this in Calc 3 many times, especially toward the end. Focus on your setup. Okay, if your setup is done incorrectly, everything you do once you get to the integration is wrong and waste of time. Okay, so focus on your setup. Focus on your setup. That's for number 4. Let's see number 5. We have this vector field, and as be part of spherical surface, rho squared equals to 2. So the radius of that sphere is rho equals to square root of 2, huh? Lying in C equals C at least 1. Oh, let me try to imagine that. So we have the radius is square root of 2, square root of 2, but the C is greater equals to 1. C equals to 1. So I think it will be something like this. Okay. So that's the cap, huh? Now orient S upward and compute. Compute double integral over S of curl of F dot ds. Now you can either compute it directly or use Stokes theorem. Okay. In fact, I will not compute it directly. I will use first Stokes theorem. The orientation is upward, right? The orientation is upward. Therefore, if we see that from above, the orientation is counterclockwise. Okay. And C equals to 1. So x squared plus y squared plus 1 equals to 2. So x squared plus y squared equals to 1. Okay. So this is equal to integral over closed curve of C of f dot dr, where the rt is parameterized by cosine t sine t 1. Remember the z equals to 1, right? The t from 0 to 2 pi. So r prime t will be negative sine t cosine t 0. Now what is f on that curve C? That will be xz, that's cosine t. The y is sine t. And the z, which is y, also sine t, the z component. Okay, so f dot dr will be negative cosine t sine t plus sine t cosine t. Oh, that's 0. Okay, so integral over closed curve of C f dot dr equals to integral from 0 to 2 pi of 0 dt. That's straightforward, 0. Okay, this is by Stokes theorem. Now, if I use double Stokes, if I use double strokes, we are actually using this surface here. Okay, notice that this surface z equals to 1 of this here has the same boundary with the boundary of the original surface S, right? Okay, the orientation is upward. So that's S2 is normal to 0, 0, 1. Notice that the nice thing about this double Stokes theorem, even if I want to do the curl of F, I just need to worry about the Z component, right? Okay, the curl of F, I just need to worry about the Z component, which is 0, 0. Right? So double integral over S2 of curl of F dot ds oriented S will be just 0. Okay, that's for number 5. Let's do number 6. Let S be the cone Z equals to 2R, where the Z is from 0 to 2. Hold on, let me try to imagine this. Z equals to 2R. Z equals to, if this is R, this is C, this is 2R. Okay, and then you rotate that with respect to Z-axis. That's what the cone look like. Okay, from C equals to 0 to C equals to 2. Okay, so this is for C equals to 2. And the density is proportional to the distance from xy plane. So the density is kz. Okay, so what is the mass of this surface S? Mass of surface S is given by double integral over that surface S, density ds, right? Let me write my density with the proper better notation. Okay, which is double integral over surface S of kz ds. Now we need to find out what is the ds. How do we interpret that ds? The surface S is given by C equals to 2R, which is 2 square root of x squared plus y squared. So Z sub x will be 2x over square root of x squared plus y squared. Is that right? Likewise, C sub y will be 2y over square root of x squared plus y squared. Now then C sub x squared plus C sub y squared plus 1 will be 4x squared plus 4y squared over x squared plus y squared plus 1. That is equals to 5. Okay, so going back, so that double integral now becomes double integral over d of k. Z is given by 2r, and then the ds now becomes square root of 5 dA. Okay, this is our ds. Okay, this is our z. And you know, I will make it cylindrical integration, right? Where the shadow at the bottom, the radius is 1, right? How do I know that, Thomas? Well, because the equation z equals to 2r equals to 2. So R must be equals to 1. Okay, that's the D. Okay, so this is square root of 5, 2, sorry, that's 2k square root of 5 double integral over d of r dA. You know what, let me just go ahead with r d theta thing. So that's 0 to 2 pi, 0 to 1, r d theta. So that's 2k square root of 5 times 2 pi times 1/3. Okay, so that's, what's that? I'm sorry, that is 4 square root of 5 pi k over 3. That's the mass. If we go on, part B, find the center of mass. Well, since S, the surface, and the density are radial, radial means this. Okay, if you rotate this surface S here with any degrees around z-axis, you will get the same shape. Likewise, when you rotate the density around the z-axis, you will also get the same. You see that this guy here is independent of x and y, right? Okay, in fact, even if you have x and y there, as long as x and y are interchangeable, like in the r here, you see r is actually x squared plus y squared. If you replace y by x, x by y, you get the same thing, right? In other words, that's symmetric with respect to x equals to y axis. In fact, it's radial, right? Because it depends on the radius only, right? Now, because the surface and the density are radial, then consequently the x bar equals to y bar equals to 0. Okay, what we want is to find the c bar. But to compute the c bar, we need to first find the moment with respect to xy plane, which is the same double integral over S, but we would need to insert z, density ds. Okay, now the z is, I think I can just go ahead with the d here. The c becomes 2r. The density is kz, the square root of 5 dA. Oh, what is my c again? I'm sorry. My c is 2r. What am I doing? So I have integral from 0 to 2 pi, integral 0 to 1, 4 square root of 5, 4 square root of 5 k r squared r dr d theta. That is 4 square root of 5k times 2 pi times 1/4. So that's 2 square root of 5k pi. Am I right? 2 square root of 5k pi. Oops, I'm sorry. That's not the answer. That's not the answer. That's just the moment. Now the z bar, therefore, will be, the c bar will be that moment divided by the mass, 4 square root of 5k pi over 3. That's what? That's 3/2, huh? Okay, that's the center of mass. Finally, I think that's the last. This is the last page. Number 7. Ooh, let's SP surface given by quarter cylinder x squared plus y squared equals to 4 for C between 0 to 4 in the first octant. Oh, okay, so in the first octant, the radius is 2. Just in the first octant. So approximately that's what it looks like. Let's help with the shadowing. Oops. Okay, the radius is 2, and then let vector field F be x0, 0. So part A, sketch the surface of S. That's the surface of S with radius 2. And this is up to Z equals to 4. Okay, part B, compute double integral of f dot ds using cylindrical parameterization. Interesting. Cylindrical parameterization. I wonder what's that again? Cylindrical parameterization. Oh, okay. So the RUV. Okay. In this case, I will use theta and z. Theta and z. If you take a look in the first octant, this is the view from above, right? This is the view from above. This is x and this is y. The factor normal to it is this one, right? So the normal factor is the normal factor is basically equals to the r, but the radius is 2. So this is 2 cosine theta, 2 sine theta z. Okay, and you will see that r u cross rv will be 2 cosine theta, 2 sine theta, comma 0. Okay, the one referred by the green arrow there, this is the one by the surface. Okay, now factor field F, which is x00. If we use RU theta z, that will just be x 0, 0. Okay, so double integral over S of f dot oriented surface S equals to integral from 0 to pi over 2, not to 2 pi because it's only a quarter circle. Okay, and the z will be from 0 to 4. Okay, and the f will be, let me just do f dot ds right away. Okay, that will be 2 cosine theta times 2 cosine theta dc d theta. Okay, it's independent of c, so I can take the 4 out. 0 to pi over 2 of 4 cosine squared d theta d theta. That is 4 times integral from 0 to pi over 2 of 2 times 1 minus cosine 2 theta d theta. Right? But I know the integral from 0 to 0 to pi over 2 for cosine 2 theta, this will be 0. So this is 4 times 2 times pi over 2, that's 4 pi. Okay. Now the next challenge is part C, where we will compute the same expression, the same double integrals, but we use this parameterization. Okay. Now, which, if you think about it, we basically have this situation. This is x here, this is y here. We make it x as a function of x and x as a function of y and z. So x sub y will be negative y over square root of 4 minus y squared. X sub c equals to 0. So x sub y squared plus x sub c squared plus, do I need to do that? No, I don't think I need to do that. I'm sorry. So the surface is normal to this normal factor here. So 1 y over square root of 4 minus y squared, comma 0. Remember, if we have z as a function of x and y, then the gradient of that, the gradient of the function, augmented function that is normal to that surface is negative c sub x, negative c sub y, comma 1, right? Okay, so if I change this becomes x as a function of y and z, then the gradient will be 1 negative x sub y, negative x sub c. Okay. Now that's the surface normal to it. How about the vector field? Vector field on that surface S will be, what's the x? Just x. Hold on. Of surface S, which is square root of 4 minus y squared, comma 0, comma 0. Right? That's the vector field. Now then, if I do the dot product, f dot ds, that will be square root of 4 minus y squared plus y over, is it? Just 4 minus y squared, because the second component multiplied by 0. Okay, only. Oh, nice. So the double integral over surface S of square root of 4 minus y squared dA. I already used A. I'm supposed to use dA here. But if that's A, then it's supposed to be the D here, right? Where the Y is from 0 to 2 and the C is from 0 to 4, right? Maybe I do it in the next line. This will be integral from 0 to 4, integral from 0 to 2 of square root of 4 minus y squared dy DC. Respect to DC, that's 4. Our issue is what is the integral from 0 to 2 of square root of 4 minus y squared dy. Now you can use trig substitution you learn in calculus 2, but I think it's easier for us to just see that, hey, you know what? This is the area, this is 4 times the area of the disk with area of a quarter disk. Quarter disk with radius 2. Okay, so 4 times 1/4 pi r squared. That's 4 pi. Okay, which gives us the same answer we did with cylindrical parameterization. Okay, that's the end of this. Let me save it and post it.